So today we'll talk about DC-coupled solar plus storage as part of Dynapower's webinar series on power electronic applications. So why are we talking about DC-coupled solar plus storage? So quite simply, this is the most cost-effective and direct method for interconnecting storage to both existing PV arrays as a retrofit application as well as new greenfield PV projects. And this is important because obviously the PV market is booming. Not only do we have a very large installed base of utility-scaled PV arrays, and currently this is over 25 gigawatts, but there's a lot of pipeline as well for utility-scale solar. And with the use cases for solar plus storage continuing to grow and gain strength, the topology chosen becomes a very important decision on how you add storage to your existing solar or new solar array. So let's go through this really quickly. Just what are these topologies? What are these options that we have when we talk about coupling storage plus solar? So the traditional methodology is the AC coupled topology. So in the AC coupled system, you have your PV inverter, you have your storage inverter, and they meet up on the AC bus. Typically, they meet up on the AC medium voltage bus where they are tied together in front of the point of interconnection. The second topology, which is considerably less common but still has a number of installations in the field, is the hybrid solar plus storage topology. In the hybrid topology, you basically have one inverter, a single inverter with multiple DC inputs, at least one for solar and at least one for storage. So you have one box, one set of controls, and a single AC interface. So there's an intuitive value and benefit here to having a single box. However, one of the disadvantages to the hybrid system and topology, and one of the reasons why it hasn't really taken off as a methodology for solar plus storage, is because once you've designed this inverter, you've designed it with a specific ratio of solar to storage. Now, in the case of the Dynapower designs for hybrid inverters, this is a 1-to-1 ratio. So for every 1 kilowatt input of solar, you have 1 kilowatt input of storage. And the problem there is that you lose design flexibility. Many systems today, solar plus storage systems today, are not built around a 1-to-1 ratio of power from the solar and the storage. And so you lose that flexibility if you wed yourself to the hybrid inverter topology. So then the question is, how can you capture the value and the benefit of a DC coupling, electrically speaking, and yet at the same time have the flexibility that you would normally see with an AC coupled array? And the answer is that you can take that DC-DC converter, which previously was inside the hybrid inverter, take that out of the hybrid inverter, and create a separate dedicated DC-DC converter, as depicted in this slide. So this DC-DC converter can then be parked behind the PV inverter on the PV bus. The simple diagram here shows a single unit, but you could have multiple DC-DC converters tied into that DC bus. So you get all the advantages, which we'll talk about with regard to DC coupling, without the limitation that you have with a hybrid inverter on the sizing flexibility. So let's take a quick step backward perhaps and address the fundamental question, well, why are we talking about solar plus storage in the first place? So the first 3 bullets summarize, I think, nicely the real value proposition of adding storage to a solar array to begin with. Obviously, there's capacity firming. If we add storage to our PV array, now we can begin to bid in to firm capacity markets. There's simple time shifting as well. This is going to become more and more important as we need to address the duck curve situation in California and emerging in other states as well. And then there's ramp rate control. And this is valuable in areas, in Hawaii is probably the best example, where you have a smaller grid where the ramp up and ramp down of your solar array has to be controlled. But these are all things that you can do with either an AC coupled or a DC coupled system, or hybrid for that matter. So what are the things that you can now do, or what are the advantages of going to a DC coupled configuration? Well, and we'll go through each one of these in a bit more detail, but to summarize, you have a lower balance of plant cost, DC coupled, than you do with an AC coupled system. You have a higher round trip efficiency when you're cycling the batteries. There's increased revenue opportunity by virtue of clipping recapture. Also, because the storage in the DC coupled configuration is parked behind a unidirectional PV inverter, there's no chance of charging storage from the array, rather from the grid, and therefore there's no chance of clawback on the ITC. Low voltage harvest is another revenue pickup that we'll talk about, as well as ramp rate control plus. And interestingly, if you are doing a DC coupled system, whether for a greenfield or for a retrofit, there should be no need for an additional system impact study based on the addition of storage. That is to say, there are no changes to the AC characteristics of your PV array when you add a DC coupled storage system behind it. So those benefits are perhaps intuitively clear, but it was actually a team at NREL that last year put numbers on the comparative values for the base case of PV only versus AC coupled and DC coupled PV plus storage. This analysis considered both cost and revenue sides. And in the final analysis, the DC coupled system demonstrates the highest benefit ratio of all possible configurations that were looked at. What's interesting is that the analysis, of course, takes into account the fact that you cannot charge the batteries from the grid because they're sitting behind a unidirectional PV inverter. This offers the advantage, of course, that you can't charge the batteries from the grid, therefore there's no chance of ITC clawback as mentioned previously. But the disadvantage now is that it removes the basic arbitrage as a use case and removes frequency regulation as an ancillary services use case as well. Despite this charge limitation and the limitation on the use cases, the DC coupled benefit to cost ratio still is superior. Let's start on the cost side and try to dissect where some of these cost savings are coming from. So let's consider, just to make the numbers round, a basic 20 megawatt case study where we have a 20 megawatt solar array coupled with 20 megawatts of storage. So in the AC coupled system, you have here in blue down below your AC coupled inverter, as well as the switchgear, the step-up transformer, and the AC collection system, all tied together on the medium voltage bus with the PV array. And this would be considered a very standard AC coupled configuration. Now, as we start to go through this and look at what happens when we shift from AC coupled to DC coupled, we'll see the removal of different major components. First, there's the removal of the AC collection system. Then there's also the removal of all the individual transformers as are typically used in the AC coupled storage configuration. Then, of course, the switchgear as well is removed. Then, of course, we're parking these the system on the PV bus behind the PV inverter. The net result of the removal of this equipment needed for the AC coupled system is a theoretical savings of $1.2 million on a typical or standard 20 megawatt array. Substantial figures, and this is why DC coupling is pointed to frequently as a more cost-effective example, or rather topology. Now, on the efficiency side, again, there are advantages with a higher efficiency on the DC coupled system. If we look at the diagram on the left, the round trip efficiency is a cycle whereby you enter the storage system through the DC converter, and then when you discharge, you go out through the DC converter again, and then out through the PV inverter. And then before you get to the grid, you go out through the medium voltage step-up transformer as well. Now, if we take a look at the diagram on the right, the AC coupled configuration, to charge the batteries, we go out through the PV inverter, up to medium voltage, step back down to low voltage on the storage side, and then are rectified through the storage inverter to charge the batteries. Then when we discharge to the grid, we go out through the storage inverter and then up and out through the medium voltage transformer to get to the grid. So the net effect, when you look at DC coupling, is you have 3 power electronic conversions and 1 transformer conversion. Whereas with AC couple, you have 3 power electronic conversions and 3 transformer conversions. Now you can take a look at the assumptions here on this slide for all the conversion efficiencies. The net result, though, is that you have up to a 3% efficiency advantage in the round trip when comparing DC coupled to AC coupled. This obviously translates directly into kilowatt hours for the developer and dollars saved across the system. So now let's shift more directly to the revenue side. We mentioned before that there are a couple of advantages from a revenue perspective of going DC coupling, and probably the biggest one, and the one that's most well understood, is clipping recapture. So this is a phenomenon, of course, where the DC PV array sizing is oversized relative to the maximum AC output of the PV inverter. And this, of course, results in situations during the day when there is excess DC capacity from the PV array that cannot be utilized by the PV inverter. This is, of course, the clipped energy as demonstrated on the graph on the left. So this is lost in an AC coupled storage system because there's no way to push that energy out through your inverter. The inverter, that is the PV inverter, is the bottleneck in the system. So when we go DC coupled, all of a sudden, we can now charge the batteries off that DC grid, capture that excess clipped energy, which is otherwise be lost, and still be able to maximize the output of the PV inverter. So if you do some quick math on this, and again, this is just an example chart from a 20 megawatt array, which happens to be in the Midwest of the US. If you have an inverter loading ratio of 1.45, you're actually going to see clipping throughout the year. And the numbers become substantial. At the end of the year, you may have upwards of 2 million kilowatt hours of lost production, which could otherwise be captured if you have a DC coupled storage system there. Now, we'll be quick to note that it is typically, from a developer's perspective, it's typically hard to justify the addition of storage simply to capture the clipped energy in this sort of configuration. So think of the clipped energy as an important value add, a very important value add, but it has to be part of a larger value stack to ultimately make a storage plus solar system pencil. And let's pause for a moment to take perhaps a quick technical diversion, which is very important. This touches on really the efficiency topic from 2 slides previously. We won't get into the gory detail here of these particular graphs, but the story is that, and the question that we're trying to answer is, well, what about maximum power point tracking? Now, for tying DC coupled storage onto this DC bus, aren't we going to disrupt or disturb or otherwise impact the max power point tracking that's taking place, typically, driven by the PV inverter? And this became a very important design criteria as we set out to develop a DC-DC converter for these configurations. And we've developed an algorithm that essentially does allow the charging and discharging of the storage off that DC PV bus without impacting the max power point tracking. And that's important for perhaps the very obvious reason that as soon as you impact your max power point tracking algorithm, you are impacting the overall efficiency of the system and impacting revenues. So that's a very important design criteria. And it's a question that comes up quite frequently. So we want to point this out that this configuration will not impact your max power point tracking. Now moving on to low voltage harvest. This is a phenomenon whereby you're able to use your DC coupled system, that is the DC coupled storage, to charge the batteries and harvest energy off the PV array during those times of the day when the PV array voltage is below the required threshold PV inverter voltage. That is the voltage that the PV inverter needs to see in order for it to operate. And put some rough numbers on this. For a typical 1500 volt PV bus, 1500 volt DC PV bus, that inverter wake-up voltage might be somewhere between 800 and 900 volts DC. So therefore, any time that the PV inverter has a voltage, but it's below that 800 or 900 volts, that's essentially lost power. And so as soon as you put on a DC coupled storage system, you are now able to charge your batteries using that energy below that threshold wake-up voltage. This could be in the beginning of the day, the end of the day, or even during a period of cloud coverage in the middle of the day. Similar phenomenon with ramp rate control, and we're referring to this as ramp rate control plus. Now, ramp rate control itself is well understood, and that's we can use AC coupled or DC coupled storage for basic ramp rate control. What we mean by ramp rate control plus is that if you are in a situation where your ramp rate up, that is your system is coming on, but you are limited in the speed with which you can ramp up your array, you're essentially clipping your PV array output. There's energy to be harvested there. And that, again, when you have a DC coupled system, you can capture that energy. And that's shown here in the graph to the right. Now, again, think of this not as a primary value proposition driver. Rather, this would be part of a larger value stack. So between low voltage harvest that we talked about a moment ago and ramp rate control plus, you may be looking at somewhere between a 2, 3, 4% pickup on the overall output of your array by going with the DC coupled system. So let's shift now and talk a little bit about what this might look like in more detail. So this is a very typical generic diagram of what it's going to look like when you DC couple storage to an existing or a new PV array. Now in this particular case, we're looking at a standard PV inverter, and behind it we've got a DC recombiner. And this may or may not be required for a DC coupled system. The recombiner is only needed if the PV inverter does not have sufficient space and protection on its existing DC bus internally. Now, many PV inverters do have these extra lugs that can be used for DC coupling, in which case this DC recombiner is in fact not needed. And also shown here, you'll see that these DC-DC converters can be operated in parallel, getting back to the whole concept previously noted about design flexibility. So you can run many of these in parallel, as many as you need, in essence, to get the right ratio of storage to your PV array size or your PV inverter size. Now, we'll show a slightly different configuration here. Now, I talked before about the fact that you cannot charge your batteries from the grid in this new DC coupled configuration. But what if we needed to charge the batteries from the grid for a particular use case, and we're not concerned perhaps about the tax credit? Well, you can actually flip everything around. In essence, here, instead of a storage system tied to a solar array, we essentially have a solar array tied to a storage system, whereby we have a standard bidirectional storage inverter. So now in this configuration, you are able to charge the batteries from the grid, and you are still DC coupled, so you're able to take advantage of all the other advantages of a DC coupled system. So in effect, you can have your cake and eat it too with this, what we'll call sort of a reverse configuration. So let's talk a little bit about the Dynapower specific converters that are applicable and available on the market today. The Dynapower DPS 250 and the DPS 375 are both UL listed converters. They have an input voltage range of 550 up to 1500 volts DC. That's both on the input side, that is the battery side, as well as the PV bus side, with a estimated CEC efficiency of 98.2%. And again, these can be run in parallel so that you can get the optimal size all the way up to potentially 3 megawatts behind a single PV inverter. So what does this look like electrically? This is a very simplified electrical diagram of the system with the left-hand side representing the input side, the battery side, and the right-hand side, the output section or the PV bus side. On both sides, you have protection, fusing and disconnect protection on both input and output, as well as DC precharge on both input and output. The onboard controller within the DPS 250 or the DPS 275 does communicate with the battery BMS and takes control of the BMS in this particular case, so that in essence the overall site controller has one point of communications interface, that is with the DPS converter. So let's look at, we've done a number of studies looking at different existing and new configurations. So let's take a look at one that represents a typical retrofit application. In this case, again, it's a 20 megawatt PV array, oversized though, so it has a 1.435 DC to AC ratio. In this particular case, there's 20 1 MVA PV inverters. So the use case for this particular application needed 15 megawatts of storage and 2 hours of storage. So that worked out to 2 DPS 375s behind each 1 megawatt inverter, which gets us to the 15 megawatts of battery storage. And there's 250 kilowatt hours behind each DPS 375 to give us the 2 hours desired. So again, because this was a retrofit application, we first had to look at the physical layout. So we took the physical drawings of the site as represented on the left and did an overlay looking at whether or not the storage would actually fit. As it turns out, it did. There was a nice laydown area from the initial installation that provided space to add the storage as depicted there on the right, where you see the 4 systems. So what you're looking at here is an inverter pad up top has 2 1 MVA inverters, and behind each one of those inverters there are now 2 DPS 375 systems. So as we jump to the next slide, we see a little bit more breakout here. On the left, you'll see what that DC storage system would actually look like. In this case, it's a skid-mounted system. On the right of the skid is the DC-DC converter. To the left is the storage enclosure. So this is an example where plenty of room, plenty of spacing, so there was not shading, and a very good fit systematically for a retrofit application. So let's pause here and just do a quick review of the benefits and reasons we're looking at DC coupled systems. We started with the lower cost. Removal of all the AC equipment improves the balance of plant costing overall. Higher efficiency translates directly to greater kilowatt hours in the lifetime of the system. And then we looked at some of the revenue side advantages as well. Clipping recapture, low voltage harvest, as well as ramp rate control. And then of course there are the obvious tax advantages. That is, because you cannot charge a DC coupled system from the grid, there's no risk of ITC clawback with this configuration. And of course, what's interesting about this is that it's applicable not just to new arrays, but also retrofits. So it really opens up for the industry a very large installed base available in the US. One thing that we've done is we've developed a calculator to help developers as they are looking at the different options and trying to optimally size the storage that would go with the new or existing PV array. We've developed this calculator directly to help developers. So the inputs that we need are listed there below. Some of the basics about the PV array, project location. We also need to understand the PPA and time of use tiers as well, if that is applicable. With all that information, we can provide a report that summarizes the revenue and cost benefit analysis for different size configurations. Thank you for your time, and certainly feel free to reach out to anyone on the Dynapower sales team if you have questions or want to dive in a bit further. Thank you.